In this video, we will learn how to describe vectors using components and unit vectors. And we will learn how to use components to do various vector operations. The x component of a vector is given by the projection of the vector onto the x-axis. Think of shining a light from above so that the light hits the x-axis at 90 degrees. If we just extend this light downward, we see that it hits the x-axis at 90 degrees. When shining the light, the vector will cast a shadow, and this shadow will be on the x-axis. You can see here the shadow being cast, and here, this is the shadow. You can see it's not as long as the vector, it's just a projection of the vector, right? Imagining the light coming down, we see that it casts a shadow, and this shadow is called the x component of the vector. Since the vector was named A, we use A subscript x to denote the x component. Similarly, if you shine light perpendicular to the y-axis, the vector will cast a shadow onto the y-axis, and this will be the y component. We see the light shining perpendicular to the y-axis and casting a shadow here on the y-axis. This is known as a y, a subscript y, the y component of the vector. How much is the x component of the vector? We see that it extends from 4 till 12, and that the direction of the original vector is pointing to the right in the direction of increasing x. So this is positive 8 is the x component of the vector. Similarly, the vector A is pointing upward a little bit, which is in the direction of increasing y, and so AY will be positive 5. We report AX is equal to positive 8, AY is equal to positive 5. Components, however, do not need to be always positive. They can be positive, negative, or 0. For example, for this vector, after doing the projections onto the x and y axis, we can see here that the vector is pointing down and to the right. So the x component will be positive. It is increasing from 4 to 8 as you go from the tail to the head. But if you look in the y direction, as you go from the tail to the head, it's going from 8 to 3. So it would be negative y component. And we see that bx is positive 4 and by is equal to negative 5. Take this moment and try to answer this question. What are the x and y components of three vectors g, h, and I? Again, this is vector g, the red one. This is vector h, here, the blue one. And this is vector I. Each square here has a side of length 1. So with that information, determine the components, whether positive or negative. Determine both the x and y components of the three vectors. Pause the video here and try and work it out on a piece of paper, and the next few slides will display the answer. And these are the x and y components of the three vectors. For example, we see that h has no y component because it is purely horizontal. It is pointing purely in the x direction. So hy is equal to 0, and its length in the x direction, it's pointing in the direction of increasing x, so it is positive, and the length is 2. So positive 2 is hx. We already know that a vector does not change when you move it parallel to itself. Using that, we see that these two vectors are the same, and as a result, their components are also the same. If we look at the x components, this one increases as we go from the tail to the head. The x value goes from 10 to 11, so it has an x component of positive 1. Even when it's over here, it has the same effect. Here it goes from 1 to 2, but it's still an increase of positive 1. Similarly, the y components in both cases would be negative 2. However, even though moving the vector around does not change the value of the components, how you choose your coordinate axes does change the value of the components. A vector by itself does not make any reference to coordinate axes. It just is. It's an arrow pointing in a particular direction. In this case, we have chosen our y and x axes like this, and we see that the vector has vx equal to positive 5.4 and vy equal to positive 5.4. The vector has both x and y components. This is now the same vector v, but I have now chosen my axes like this. In this situation, vx is positive 7.6 and vy is 0. There is no y component. You might say, well, this is a natural way of picking your coordinate axes, but in fact there is no natural way of picking the coordinate axis. We pick different coordinate axes according to the problem, and in different problems, different axes and different orientations of those axes would be useful. So there is no single right way of choosing the axis. And as a result, the vector remains unchanged, but the components that describe the vector depend on the axes that you choose. As an example, think of a diamond. The intrinsic value of the diamond doesn't change, but the number that you assign to it will change depending upon whether you are using US dollars, British pounds, rupees, yen, or any other currency that you might care to think of. Each of those is a valid way of describing the diamond, but each of them gives you a different number. There is no single right way. As a more physical example of a case where there are two reasonable choices for coordinate axes, consider a ball rolling up a ramp. The velocity of the ball is directed parallel to the slope of the ramp, and the acceleration due to gravity is directed downward. One possible choice of the coordinate axes involves setting the axes like this, in which case the acceleration due to gravity has only a y component. But the velocity has both an x component, a positive x component, and a positive y component because it is moving to the right and up. However, another choice would be using tilted axes like this. In this case, the acceleration due to gravity would have two components, but the velocity would only have an x component. There is no velocity for this ball in the y direction because it is moving parallel to the slope, which is parallel to the x-axis. As long as it does not leave the slope, as long as it does not bounce up or dig into the slope, then there is no movement in this y direction. There is only movement in this x direction. And so the velocity would only have an x component and no y component. Later on, when we actually get to solving these problems, we will see that in fact this tilted coordinate axis is simpler for this particular problem, but it may not always be true. So there is no always correct way of choosing coordinate axes. Look at the problem and decide. The components of a vector, if we think of a vector in three-dimensional space, would be denoted as ax, ay, and az, usually put in simple parentheses separated by commas. But these components are simply numbers with units. Sure, they can be positive, negative, 0, but we have just said that the coordinate axes could be different. So just having numbers doesn't really tell you about direction unless you know how the coordinate axes are set up. So where has that vector nature of A gone? What would tell us about the coordinate axes? So AX is the directed length or the component of A along the x-axis. It is the projection or shadow of the vector A along the x-axis. But in which way does the x-axis point? Note that we will use unit vectors. So in the xy plane, for example, we would write vector A is equal to AX times I hat. All right, this is called I hat, plus AY times J hat. I hat is the unit vector pointing in the direction of increasing x, and J hat is the unit vector pointing in the direction of increasing y. We use the letters I, J, and K with hats on top to represent the unit vectors pointing along the x, y, or z axes respectively. Why do I keep calling them unit vectors? A unit there refers to unity or 1, and it simply tells you that they have a length 1. Okay, so the length of the I hat vector is 1. The length of the J hat vector is 1. And it is a convention to put this little hat on top whenever you are dealing with a unit vector. Thus, AX I hat is the x component vector of A, and AY J hat is the y component vector of A. So just AX is the x component, but if I write AX I hat, it is the x component vector, right? It is no longer just a number with units, it also has a direction thanks to I hat, because I hat tells you in which direction does the x-axis point. So just to recap some of the terminology, if we have a three-dimensional vector A with components AX, AY, and AZ, we write it out like this, and we say that this is denoting A in the unit vector notation because I have written it in terms of components and unit vectors. AX is called the x component of A, AY is the y component, and so on. And these are collectively called the vector components of A. But once we multiply it by I hat and J hat and K hat and so on, AX I hat is the x component vector. So AX I hat, AY J hat, and AZ K hat are collectively known as the component vectors of A. Vector components like AX, AZ, etc. are just numbers with units and signs. By themselves, they are not vectors. The component vectors, however, do carry a vector. Okay, so they are themselves vectors, they have directions, and if you add them all up together, they add up to the total original vector. Notice what is happening. We are saying to move in the direction of the vector A, I want you to step so many steps north, so many steps east, and then say dig into the ground for such a distance. It's like treasure map directions. Okay, I hat, J hat, and K hat give you north, east, and vertical up, down, and AX, AY, AZ tell you how far to move in each of those directions. Putting all this information together recovers the original vector. And usually if we just use the word components, we are referring to the vector components ax, ay, and az. So we can see that putting together both components and unit vectors, vx I hat, vy j hat, putting that together gives you this vector. Putting that together gives you this vector, and putting both of those together would give you this, the total vector v, which in this case is in the xy plane. What would I hat by itself look like? Zooming in a little, we can see that I hat would just be a vector of length 1. Similarly, j hat would also be a vector of length 1, but pointing in the direction of increasing y. This would be the j hat vector. Here's another problem. In unit vector notation, what are the vectors d, e, and f? So now remember, you need to write them in the form of components times unit vectors and add up all the three pieces. Except, of course, in this case, since all three vectors are in the xy plane, there will be no z component for any of these vectors. So take a moment, grab a piece of paper, and write out the expressions for these vectors in unit vector notation. And the next few slides will show the answers. So now we have two equivalent ways of describing a vector. We can talk about its magnitude, that is its overall length, and the direction, which is, say, the angle it makes with the x-axis. Or we can talk about its x component and its y component. How do we convert between these two descriptions? If your vector lies in a plane in 2 dimensions with only x and y components, we can use the following relations. The magnitude of v is given by the Pythagorean theorem. You take the x component, square it, the y component, square it, and then square root the whole thing, and that gives you the magnitude. Similarly, the tangent of the angle theta would be given by vy over vx. Again, using that triangle, we can see that Vx would be the magnitude of V times cosine of the angle, because the magnitude of V is the hypotenuse. And similarly, Vy would be magnitude of V times the sine of the angle, because again, the magnitude of V is the hypotenuse. Looking at this right angle triangle, once again, we see that the magnitude of the vector gives you the length of the hypotenuse. The x component is the adjacent side to this angle, and so would be related to the cosine of this angle. Similarly, the y component is related to this side, and this side is the opposite side to this angle, and so the length of this side would be related to the sine of this angle. Here is another question. What is q in the unit vector notation? Take a moment and jot down the answer. And here is another question, the same vector, but this is a multiple choice question. What is the magnitude of the vector q? Take a few moments and calculate that. Your previous result using the components of q should help you get the answer here. The next slide will show the answer. So we can see that having determined qx and qy, we simply square them and add them and square root them to get the magnitude. Because of the squaring, even though these components are both negative, once they're squared, the negative sign goes away. Remember that the magnitude is always positive or at most 0. Now that we have a component description of vectors, operations like adding and subtracting become simple arithmetical operations. For example, adding a plus b is simply a matter of adding them component by component. You add the two x components, you add the two y components, you add the two z components, and don't forget the unit vectors. Similarly, you can scale each of those vectors by multiplying them by simple numbers. So 3a minus 2b becomes, in component form, this. One more question. A is given in unit vector notation like this, 1i hat plus 2j hat minus 3k hat, and b is given as 3i hat plus 4j hat. And the question is, what is 6a minus 5b? Pause the video here, take a few moments and calculate the answer. And the next slide will show the answer. Alright, that's it for this video. I'll see you in the next.